Hello, welcome and an excellent evening. Tonight we have the Pico DRAM tester by TubeTime, that is Eric Schlaepfer, who also brought us a ton of other interesting stuff like the Snark Barker Sound Blaster clone, the original Adlib replica, and a ton of other projects. And there are a lot of DRAM testers like these. This is based on an Arduino Uno, and it is a DRAM tester that can test both 4164, which are often used in older C64 boards, and 41256 DRAM. Both 1-bit RAM chips, 64K and 256K. But of course, there are also other variants like 4-bit ones, 4416, 4464, 44246, and older stuff like 4116, which I think uses 12 volts and -5 volts for biasing. Stuff like that, more rare or more older things. And this here also doesn't test the timing of the chips. So if a chip is marginal according to the timing printed on it, like 150 nanoseconds or something, it won't tell you. So these are fine and fun and quite good for a quick test if you have a dead Commodore 64 and your desk test or something shows you a certain RAM chip to be bad. But it's of course nice to, if you were able to test also something like the timings. And that's where this comes in. It uses the Raspberry Pi Pico 2, which is the upgraded and much faster version of the Pi Pico. It has a little LCD display for interface and encoder for selecting the menu and a push button. Two DC-DC converters for providing 12 volts and -5 volts. And a couple of sockets will be here. These are the sockets for inserting different kinds of RAMs. It says here which ones, so you have different sockets so that you don't need to put any jumpers in or stuff like that. And this is like the very luxurious version of a regular DRAM tester basically. There is input here, +5 and ground, that you can hook up to your bench power supply, or you can power it via the Pi Pico. But I think I heard that it's supposed to be best powered from a bench power supply or something similar. Let's see on the back. It says here quite a lot of nice thanks. Special thanks to BitSavers, MX Shift, Ian Polpo of PicoGas fame, TD Linux, Jay Haluska, RF Programmer, Platypus with Cheese, NanoCat, Cave Johnson 1337, the Girl Geek, and the rest of the streaming crew. Okay, so I guess he probably designed this on one of his live streams. It totally passed me by. I didn't notice this. I'm not sure if he advertised it on his Mastodon account. He writes quite a bit of stuff there, but I think he uses some other social media channels more. So I might have missed out on that. I saw it on More Fun Making It. He showed this off a couple of weeks ago, I think. And I thought, wow, this could be very useful. Not quite sure if my TED RAM will actually be usable in this. Let's have a look. So here are the old RAM chips from my Commodore PET, and I think these use 12 volts. These are 4108, which are actually not supported. I think they would basically fit in here in the 4116. And the question would be if they could be made to be supported, because they basically just have less address lines, one less address line than the 4116. That would be something I should inquire, because the rest should be perfectly compatible. Interesting. Yeah. So I ordered a bunch of these and made a pool order for the forum. All the other kits I have already sent away. And now I can finally assemble my own kit, I would say. So here's everything that we need. Here is the LCD display. I will put this to the side because I think we'll put that in almost at the last point. So there's this. We might have to, we will have to get the BOM out, the bill of materials, because I don't know which resistors go where. And I think we might want to solder in the Pico first, because once we have the resistor arrays, here, the 4 resistor arrays in, it's probably very hard to solder this one in place. Doesn't use pin headers to install this thing, so which is fine. I did the same thing on the original Pico Gus, which also used the Pi Pico, the Pico 1. So yeah, let's quickly record this in, well, accelerated mode. And then proceed. I will take the printed BOM, I think I have it, over there, yes. And then we can hopefully get this assembled pretty quickly. All right, I think this is the Pi done. That's pretty nice. Okay, let's continue with the resistors. Here's the bill of materials. We have 6 resistors, 4.7K. Those are R4, 6, 7, 8, 9, 10. Let's take those first. Okay, these are the first couple of resistors in, and yeah, seems to be working fine. Gonna populate the rest of the resistors and the little bypass capacitors, and after that we can progress to the resistor arrays, DC-DC, and the rest of the components, especially the ZIF sockets. So the capacitors are in, all the resistors are in the resistor packs. What I didn't show before was the little SMD diode here. I put that on when I received the boards, basically, because they're so tiny they get lost. It's this super tiny little package here. Then we have these DC-DC converters. This is the ITR 0305S12, which should be the 12-volt one, and this is the RFM 0505S, says in 5, out 5. So that's the 5 volt one, which is used to generate minus 5 volts actually. And my iron was going to go to sleep, but not that fast. So I put in both DC-DC converters, and then we're gonna take a look if they are sitting flush with the board. This one doesn't. Now it's better. This should be nice. We don't want them to wobble around. Right, and then we have this transistor, I guess. And it seems it goes in like so. I'm wondering if I should leave the legs a little bit longer. Probably like this. Next up, we have this capacitor, I'd say. Maybe? Probably. What about the display? Ah yes, I think I will do this a little bit later. Okay, I think I'm supposed to put something in here that this can rest on. Maybe, so that it doesn't flop around so precariously. I might put in just a couple of these pin headers. They might be just fine for that purpose. Yeah, I think those are nice. Do I have more? Somewhere I do, but not here. Let me fetch a couple. Or let me do that in a second. I'm first gonna put in all the ZIF sockets and the switch and the encoder. And these are so not 3M text tool. They look like that. There's even a patent number on there, but it says TFX TDOL. Well, I guess this way you can't be sued by 3M. Original 3M text tool sockets, I think most of them are out of production. And if you can find them, they're like 10 to 20 euros a piece, which would make this extremely expensive. And these here, you can have them for around 2 euros at most. Very nice detail. There's the pinout of all the chips down here, so you can probe it with all the address lines, data bits. Alright, I got almost everything in here except for this socket, and I must say the quality of these is of course not superb. And it was stupid that I put this in last because it's the middle one. And you have to carefully wiggle it around and bend the pins so that they align with each other pairwise, else you won't get it in here. Yeah, so put this in first, I want to say. Don't do it like me. So there are traces going to these things here, so I'm gonna think that this is for a different display, the pinout, and I'm gonna put some Kapton tape down here, which will isolate the electrical signals. See, just like so. And now it's electrically not connected. I'm gonna solder down the proper pins here. And there we go. I also put in these probe pins where you can feed in the 5 volt, and you can also measure and pick off the extra voltages like -5 volts and 12 volts, so you can check, I guess, if the voltage rates are great. That's it. Now we have to flash this thing. We have to attach it with a micro USB to our computer and drag and drop the firmware into it, because that's how the Pico 2 works. So let's try this out, and afterwards we come back here and test some RAM chips, I would say. This is the Pico DRAM tester Git repository, and we can download the firmware here. It is in the firmware subdirectory, and we can say, please give us the raw file. And if I'm going to connect this blank Pico 2, it will appear over here in the Finder. Same goes for Windows and Linux. It will connect as a mass storage device. And I can just drop the firmware on here, and it will reboot and work as expected. And I'm already seeing the thing here. Amazing. I think because it's so easy, we can just switch back to the main camera. So let's do that. There we go. It has this lovely Windows-like, Windows 3. No, not 3.1, 95 like interface, which is really cool, and the encoder is really clicky. Let's check a couple of RAMs. Let me pull up the light a bit so that you can see what I'm doing here. This is a TMS 4416, so this is a 4-bit 16K RAM chip. 4416, I think that's up here, 4416. That should fit in here. Yes, it does. We choose it here, 4416, 16K times 4. And this is supposed to be 150 nanoseconds. Turn on external supply afterwards if used. Okay, but we don't have that. And this chip has passed. Great. Let's try this again, but let's test it on 120 nanoseconds. And it passed even that, so it works also at 120 nanoseconds, which is nice. We have a 41256. 41256 is here, down in the corner. 41256. And this is supposed to be 100 nanoseconds. Failed. Ooh. That's interesting. Interesting. I'm not sure where I took this from. It has slightly bent pins. Maybe it's a broken one. Let me squeeze it a little bit. Where did I get this from? 41256. No, that's correct. There's one cell that is marked bad. So 41256, 100 nanoseconds. Oh yes, one cell is bad. Interesting. Oh wow, that's nice. I didn't know that this one was bad. Let's give it more time. Let's say maybe this works at 150 seconds. Oh no, there's now 2 failed ones. Let's test again at 100 nanoseconds. At 100 nanoseconds there's only 1 failed cell. I'm sure you can see that. Let me pick this up. Right down here in the corner there's a failed cell. And we can try this again at 150, slower timings. Then we get one here and one here. Okay, so this seems to be a bad chip. Maybe it isn't really bad. I heard from the video that more fun fixing it or making it showed that sometimes this gives wrong results, as does every tester, I have to say, but it does give pretty decent feedback, I think. So here we have 81256. I'm wondering if this is pin compatible to the 41256. I will put this here and we'll check that in a minute. I do have some 4164 here, which we didn't test yet, I think. 4164 at 120 nanoseconds. 4164 at 120. Oh, this also failed. That's interesting, at the same spot. I smell something fishy here. Could this be an issue with the tester? One way to find out, let's take more of these. I have quite a bunch of 4164s. Same here, 120 nanoseconds. Yeah, they say all fail in the same manner. I'm wondering if the tests for these chips are not quite working. What else do we have? I have so many things. These are like fake relabeled ones. They are probably 4164s, but with relabeled Matsushita Panasonic. That's totally relabeled. They're supposed to be 150. And it passes. So that's interesting. So these, this is not the one. These Samsung branded ones, they seem to have failures. But I'm sure that I used them. 4164, 120 nanoseconds. And they all fail at that same position. I'm wondering if there is a bug regarding certain things, but it's good to know that I can test these relabeled ones and that some of them turn out to be good. Here we have a 71C464. I would assume that this can't be a 4464, I guess. Oh, it could be. Yeah, so I have to look these up if they are compatible. But very excellent that I can test relabeled ones. Another relabeled one. Oh, shows the same issue. 4164. At 150 nanosecond it works fine. Oh, so when I test it on slower speeds, it works fine. Which is okay because it says 150 nanoseconds, even though it's relabeled. Let's test the Samsung one again on a slower speed, on 150 nanoseconds. No, still failure. What about 250 nanoseconds? Aha! Here it works. So maybe these are relabeled ones and they're actually slower. Let's go to 200 nanoseconds. Working fine. So, interesting and excellent news actually. These might be relabeled too. I'm gonna look up the 81256 and the 71C464 and see if they are compatible to anything here. I do have these 1 megabit chips, I think, 41C1000, but I think this thing doesn't test that. It goes up to 256K, so we can't test the big chips, let's say. What else do we have here? I think these are C16 ones, 48416. Yeah, we can also put them here and I look up if they are compatible. One moment, please. Oh well, I think the 81256 should be compatible, so I'm gonna just pop it in here. I don't even know where it came from, so it should be 41256. And it says 100 nanoseconds, so let's try it. And it seems to be working just fine, but it takes quite a long time, probably due to the size. But the animation looks quite nice. And it passed. Well, that's good news. So they are compatible. The 71464, I would guess, should be compatible to the 4464, I hope. Otherwise we're gonna fry this. But I think this should be compatible. 4464 at 80 nanoseconds it says. Let's see. And it failed. Interesting, but it worked for a while. Let's give it a little bit more slack, 100 nanoseconds. And that is actually looking pretty decent. Yes, at 100 nanoseconds it works. Okay, this gold star chip seems to be fine, maybe out of spec. Maybe this thing here is not quite correct. And this is a 48416. I would guess this is a 4416 4-bit wide because it's relatively large. It can't be a 4116, which also uses the plus 12 and minus 5, I think. So we're guessing this is a 4416 and at speed of 120 nanoseconds. Looking good, and it passed. Okay, so even the more obscure DRAMs can be tested quite well. I think this is an awesome tool. The sockets, this socket here is crappy. That was the one that I had problems putting in, and it looks different from the other three. It looks more like this one up here. So yeah, the sockets are an issue. They are, the 3M sockets are great, but these are just cheap copies. What I wanted to know is if you can put in 4108 in here, but that would require adjusting the firmware. Let me have a quick look around the source code and see if there's any simple way to define that there's one address pin less or something. I have taken a look at the source code of the firmware for the Pico DRAM tester, and it's all here in the GitHub repository, and
the main things are in the pmemtest main program. Then there's a so-called PIO patcher, and there are a bunch of PIO programs. What those are, I will explain in a couple of seconds or minutes. And the issue that I found, and or not me, but actually the author, Eric, we talked on Mastodon, where incidentally you can also follow me, chaos.social/root42, is the following: that some of the chips that I have, like the Siemens chips, but also the Samsung chips, they have something called, where is it? The write command hold time. This is a value, a timing value, and this is at minimum 30 to 45 nanoseconds, depending on the speed of the device. 100, 120, 150 nanoseconds in this case. I'm not even sure what exactly it does, but it will be somewhere here in the timing diagrams. I'm guessing that it has to do with writing to a memory location, I guess. So probably somewhere in here there will be the TWCH, but I'm not seeing it. Here it is. Here it is. It's a page mode write cycle. Okay, whatever that means. I'm not an expert. But this value here is higher on these chips than on others. Others seem to have a minimum of 20 nanoseconds. And if you go into the source code, which we are doing here, and I'm gonna try and make this a bit easier to read, hopefully, if I manage to do this exactly like so. This is one of the PIO programs. PIO is a special part of the Pi Pico, the programmable I/O. It's small state machines that have a very simple machine code, so that's why this looks like assembly, with just a couple of instructions. I'm not sure how many, but like a dozen or maybe 20 instructions, much more reduced than other regular general purpose CPUs. And you can have like super high speed toggling of the GPIO pins with that, which helps you to interface with timing critical stuff like legacy buses. For example, the Pico uses this to interface with the PC's ISA bus. And here we use it to actually write and update the DRAM. So there's all this kind of stuff happening to, and I think this is probably kind of nanoseconds, I guess. A timing that Eric wrote down here. I'm just guessing, but something like that. And further down, after this whole assembly stuff, there's a bunch of setup routines and data. And especially, there is this array, and that's in every PIO program for the different RAM chips. This is for the 4164. And there are a bunch of timing numbers for the different speeds of the chip. And for the 120 nanosecond chips that I have here, there's this magic number here in the fourth place, which determines the delay for the TWCH timing that you just saw. And when you switch this from 2 to 7, suddenly it starts to work with these, because it increases very slightly the delay that's happening. The real thing is much more complicated. Eric said he has an Excel sheet that calculates these timings. That is a whole big mess, he said, so he probably won't release it. But maybe there will be some update to the firmware, hopefully, with more supported chips, let's say. And at least for me, updating this line here helped for this particular part, basically. I'm not sure about slower chips, if there's something to do there. But anyway, if we search for this thing here, this is being used in the setup routine of this file. And there's a function called PIO patch delays, and that's a bit interesting, so we're gonna look at that. PIO patch delays is the function that uses this data. It gets this stuff here passed into it, and it will take the current PIO program that was the machine code at the top here that gets assembled into a data blob, and this data blob is stored in current PIO instructions. And it's a very short program. It's at most 32 instructions long. That's how long these programs can be. And it's gonna patch them. Indeed, it does patch them by getting the current instruction there and masking this with EOFF. And EOFF, if you take a look at that, which we can do by calling up the calculator, down here, let's make it larger. EOFF is exactly like this. The first 3 bits set, then 5 bits not set, and the rest of the bits is again set. And now we're looking into the instruction set for this state machine of the Pico. And here I have the datasheet in quotation marks because it's like 900 pages long or something. But somewhere very far at the back, there's the instruction set. These are all the assembly instructions that you have. Jump, wait, in, out, push, move, pull, and 2 other move operations, an IRQ and a set. But if you take a close look, the 5 bits that are set to 0 or masked 0 here in this line, they're called delay side set. With the delay side set bits, depending on how the side set count register is set in the Pico, you can either introduce extra delays into these instructions, that is, make them slower, perform slower for slower chips, for example, or depending on the register, some of the bits, the most significant bits, will be used for toggling GPIO pin directions. We won't talk about that part, but Eric here uses all 3 bits to introduce additional delays, up to 31 cycles, kind of. I'm not sure if those are cycles, but you can basically fine-tune the timing of your instructions, of the signals, so that you will get exactly the timing diagrams as shown here in the datasheets. And those timing diagrams vary from manufacturer to manufacturer. They all say we have 120 nanoseconds parts, but then something like the TWCH will be shorter or longer depending on the manufacturer. And you can look those up in these datasheets, historic datasheets from the 80s and 90s for these chips. And that's where all the magic is. It would be nice if either you could choose different manufacturers in this tester. That might happen. I mean, you could just produce more PIO programs and put them there. Or if there would be subsettings for more relaxed timings where you don't take the minimum of 20 nanoseconds, but say, okay, here we're using the maximum actually that is allowed, and we're testing that for a more relaxed testing. So you could have a strict testing and a relaxed testing. And if the chip tests fine on the relaxed setting, then you know, okay, it's probably good, but it's a bit on the slow side, even if it fails on the strict minimum testing. Okay, that's that. What I also tried was introducing a test for the 4108 that I have, but I can already tell you it doesn't work. I just copied the 4116 program and just changed it so that the naming is different and that the mem size is only 8192. But the issue here is the 4108 chip is actually not a chip on its own. It's just a rebatched 4116 where one half of the chip has at least one error, one fault. And you can only use the other half that's still good. And Commodore selected exactly those chips where all the same halves were okay and put them in the pad. There's now an issue on GitHub for support for these half-broken chips because Sinclair and Commodore used them quite a lot of machines. So it is nice to be able to check the full chip and just get told, okay, the lower half is still fine and the upper half has an error or the other way around. So Eric is aware of that, and fingers crossed, maybe we'll get something like that. But that's what I wanted to show you here in the code. I must say the code is very clear and concise. I don't fully understand the PIO stuff here yet because I never programmed the Pico PIO, but maybe that's a good reason to start understanding it. I mean, it's a very reduced instruction set, so it should be relatively easy to learn. And it definitely looks very interesting. But the code is there for you to look at. The datasheet for the Pi Pico is phenomenally detailed, so there's everything in there that you want and it's for free. Yeah, so check it out. But let's go back to the hardware one more time and wrap this thing up.
Let's have one last look at the device. And I have the Samsung 4164K and 4164B-12 in here, 120 nanosecond part, and this would fail before, no matter what speed I would be using, or I think it would maybe run at 200 nanoseconds or something. So if I take this, put it into 120 nanosecond mode, it will work just fine. This definitely is working now. I do have at least one chip here that does not work, and it could be that this is actually marginal. It fails with the March B test already, and I think I can't put it into slower mode either. Actually, it does. At 200 nanoseconds it works, so this seems to be even worse in its timings. So yeah, if something fails on this device, it might be that it is not as good as the original part, but has some slightly worse timings, let's say. And that is something where I, as I said, would like to see a relaxed timing, where the device uses the maximum allowed timings from the original datasheet, just to see would it work under very optimistic conditions, let's say, okay? And you could still test it with the worst settings and figure out, okay, it definitely has issues. Yeah, that would be nice. I also found these 81256, and I think those are 41256, but from Fujitsu. So we can test that as well. Those are 100 nanoseconds. Also works just fine. It takes a while because it's 256 kilobit, so 4 times the size of the previous chips. And I must say, this is an awesome little device. It is more expensive than one of these cheap things. You can build one of these for like 20 euros roughly, with a clone Arduino board and this shield here. I think this will be 20 euros, maybe slightly more, but roughly that. And you can reuse the Arduino for something else if you don't need it for testing, but it only does 2 different kinds of chips. There's also one other chip tester out there that I don't have, which tests the upper lower half thing and also supports the -5 and +12 volt supply chips as well. Not sure about its price, and this here comes in at 50-ish euros raw materials, basically, in a high quality. These are all high quality components. You can, yeah, well, sockets of course not. Those can be 20 euros a pop, but these are the cheap Chinese clones. But all the other components here are pretty decent, and you can probably save a bit money, but roughly 50 euros. And that's pretty neat for having support for so many things, and there might be support for other chips as well in the future, which have compatible pinouts. And it's a work in progress, obviously. but this is much cheaper, obviously, compared to the Backbit chip tester or the Retro Chip Tester Pro, which can do much more. They can test CPUs, they can test special purpose chips from Commodore and logic chips and I don't know what, but those are a couple €100 at least, between 200 and 300 euros, I think, with the adapters and stuff and importing and I don't know what. So I can buy a couple of these, and I do have the TL866 for at least roughly testing logic chips. So between this and the TL866, there are only the custom Commodore chips and similar things that I can't test with my current setup for a much lower price, let's say. But yeah, I think that's all I wanted to show you. Share, like, and subscribe, the usual stuff. Please leave a comment. There are a lot of nice Pi Pico projects out there, especially in the retro community, but also other stuff. If you want to build one of your own, the link is in the video description. And yeah, I think that's all. As I said, please do follow me on Mastodon, chaos.social/root42. I post a lot of updates there. Otherwise, you can also join me on Patreon. Usually every video will be available there 3 days early. And other than that, see you in the next video. Have a nice time. Bye.